Okay, we talked about tosylation of the alcohols, and we talked about the benefit of that. When you do tosylation of the alcohol, the leaving group of hydroxide or hydroxy leaving group would change to a bulky leaving group of tosylate. And then when under what or for which type of reaction you need a better leaving group? Do you remember that? That was a question from last class as well. In what type of reactions you need a good leaving group? Am I getting responses in the chat or? SN2, both SN2 and SN1, and also for the for elimination reactions also, you want good leaving group. Okay, if you have a better leaving group, it would be faster reaction. So SN1, SN2 reactions, they would benefit from a good leaving group, and mainly SN2 reactions. So if you have a very good leaving group, then the SN2 reaction it would be possible. I did talk about the type of reactions, but I didn't show you the table with all those reactions that a tosylated alcohol can go through very easily. So if you want to look at the mechanism for this for this reaction, like for the substitution of the and the elimination type reactions, for both of them, we need a good leaving group. So for just the mechanism for the tosylation, you see the arrow is coming always from electron rich to electron poor. So S is electron poor here, is partially positive center here, and then the pair of electrons, so it is going to come and form bond. When it forms bond here, oxygen would get the positive charge. So you are going to make this, then the hydrogen is removed from using a solvent. So deprotonation, so nucleophilic attack, and then deprotonation, it follows by the deprotonation. So you can see this deprotonation is happening. Then you have a stable compound, and in this stable compound, which is a tosylated alcohol, now you have alcohol with tosylate group instead of the OH group. So this can be replaced by any good nucleophile in SN2 reaction, or it can be replaced, it can leave, and then you can do like elimination reaction. So in SN2 type reaction, basically that's what you have, OTS instead of the OH as the leaving group. When nucleophile comes in, then the leaving group is going to leave. If the OTS leaves in E1 mechanisms, if the leaving group leaves and the base or the solvent deprotonates the adjacent carbon, it was right here. So with this leaving group is leaving and the base is deprotonating adjacent solvent as the adjacent carbon, you are going to get carbon-carbon double bond, and that is the elimination reaction that alcohol can go through. So one reaction for the alcohol, which is elimination, there are two possible ways to do elimination. Either you protonate the OH to change to H2O, and then that would make the OH better leaving group. The other way would be to tosylate the alcohol. You change the OH to OTS and then get that as the good leaving group. By removing hydrogen from adjacent carbon, you are going to have the double bond forms. Now, let's say if you have this is covered in organic 1 already for you. I just want to emphasize on that. Again, let's say you have your C and then plus charge here. When the carbocation forms, okay, carbocation is very unstable. Now you have two ways to stabilize this, because carbon with less than 4 bond is a disaster for the carbon. Carbon cannot have more than 4 bonds, cannot have less than 4 bonds. Under both conditions, is going to be very high energetic and very unstable. So one way you can satisfy the carbon is to bring a nucleophile. When you bring a nucleophile, what makes a nucleophile to be a nucleophile is either has pair of unshared electron or it has a negative charge, which means is electron rich. So when you bring a nucleophile, forms bond with the carbocation, then the carbocation becomes a compound and becomes stable, just like this structure that you have here. If you do not have a nucleophile or the condition of the reaction is favoring like a elimination reaction, and that one of the condition of that, what condition changes or favors elimination reaction, if you recall from chapter 7 of the organic chemistry, is like the effect of the solvent. What type of solvent are you do you have? Is it like a polar protic solvent? Is it an aprotic solvent? Because aprotic solvent, it favors Sn2 type reaction. And then you have, when you have a carbocation or elimination for the, you want protic solvent. If you have like alcohol base solvent, is going to favor elimination. High temperature, it would favor elimination. A strong base, it would favor elimination. Can you tell me why a strong base would favor elimination? Or how a strong base favors elimination? A strong base favors elimination. A strong nucleophile favors substitution, but a strong base would favor elimination. In order for elimination to take place, when you have a hydrogen here, you have to bring a base to remove the hydrogen. When you remove the hydrogen, or when you bring a base to remove the hydrogen, you are not removing H minus, right? You are not removing hydride ion. You are not removing hydrogen free radical. You are not removing H2. These are not what you are removing. You are removing H plus. And when you remove H plus, when you bring base, is going to, base is looking for acid, and H plus is the acid in here. You remove the H plus. Now, what happens to this pair of electrons? This pair of electron doesn't go with hydrogen, so this pair of electron is going to drop in. When the pair of electron drops in, then you get your CC double bond there. So basically, when you remove the H plus, you are going to create here a carbon with negative charge, and then an adjacent carbon, you have positive charge. This positive charge is going to be satisfied with this negative charge by bringing the pair of electrons to the center, and then they are going to share, and you get rid of that plus charge. Because until you have that plus charge, you don't have a compound. It's intermediate, is a carbocation, it is very unstable. So for substitution reaction, you need the strong nucleophile. For elimination reaction, you need a strong base. And both of them require good leaving group. That's why you start with alcohol, you tosylate first. By tosylating alcohol, you're changing alcohol to our OTS, which is the tosylated alcohol. You have better leaving group now, and it can be replaced by nucleophile, or it can leave and change to leave and initiate a elimination reaction, which is production of the alkene as a product. This slide also talks about the same, is just saying substitution. If you want to do like substitution reaction by Sn2, this is a Sn2 reaction, then in Sn2 reaction, remember that umbrella or London, not the London, is Walden, sorry, Walden inversion that happens. What it means that the attack of the nucleophile toward the nucleus is a back attack. means that if the leaving group is leaving from the right side of the molecule, the nucleophile is coming in from the left side. And if you have if you have a chiral center, your compound, you start with like a chiral compound that you have a chiral center, the configuration or stereochemistry of that is going to change. If you start with S, it will change to R configuration. So you are going to get the enantiomer of the, or the opposite. If you start with the S, you end up with the R product, and that is the inversion in the stereo chemistry of it. So OTS, why is a good leaving group? What makes a good leaving group, a good leaving group? The stability of the group after it leaves the molecule. So if you compare Cl- with Br-, which one is the better leaving group? Can you tell me which one is the better leaving group? Br, thank you. The size of the Br is good because it's going to handle that negative charge better. So it makes these Br a better leaving group. Now, which one is a stronger base? Br- or Cl-? Which one is a stronger base? In order to find out if this is a stronger, Cl- is stronger or Br is a stronger base, what should you start with? Br is a stronger base or better leaving group? I'm looking for your answer in the chat box, but what would you consider? You should consider where they are coming from. Cl- is coming from HCl and Br- is coming from HBr. When it comes to acidity, HBr is a stronger acid than HCl. A strong acid would yield to what? Weaker conjugate base. Weaker acid, it would give you a stronger conjugate base. So Br- is going to be weaker than a Cl-. So in this comparison, I'm comparing the basicity, which one is a stronger base or weaker base. This case, Cl- is going to be a stronger base, but HBr is a stronger acid. So if you have acid-base conjugate, the stronger the acid is, the weaker the base is. Weak base or weaker base is a better leaving group because it's not reactive, it's stable on its own. So what makes the tosylate to be a good leaving group also is the stability of the leaving group. After it leaves, it's going to give you, it makes like 3 resonances. And if you have 3 resonances, it makes the leaving group very stable. Okay. These are the reactions that I was talking about. And I said, if you tosylate the alcohol, then you can make that tosylated alcohol with the tosylate to go through multiple like Sn2 type reactions. And then you would, if you bring in hydroxide, it would change it back to alcohol. If you bring lithium borohydride or sodium borohydride, if you bring hydride, basically ion, it replace that. This is a nucleophile, is going to replace the OTS, and it would give you alkane. Pay attention to this reaction because when in reduction of the alcohol, you're dealing with this reaction again. So you can replace OTS with ammonia and you get like a primary amine. You can replace it with the alkoxide, you get ether. And then with the halide, you can get alkyl halide. So because you have a good leaving group, you can make it go through Sn2 reaction by bringing different nucleophile. Okay. Do you remember different types of reactions so far? what reactions you have learned about alcohol so far. You can type it. Okay, the Cl that you have in the chat, just to make sure that it's correct, Cl minus is going to be a stronger base. If you mean a stronger base rather than better base, that is correct. So a stronger base. And then Br minus is a weaker base, but it is a better nucleophile. If that's what you meant, that is very good. Okay. Can you name so far the reactions that you've learned? You can use the chat. What you have learned so far? Do you remember? You remember the reactions? Any reactions? Oxidation, very good. Grignard is to prepare alcohols, is not the reaction of alcohol. Okay. Oxidation, and then changing to substitution. But when you do substitution of the alcohols, you have direct substitution or indirect substitution. So you learned about like the indirect substitution. First, you have to do tosylation, and then from the tosylate, you can change it to the any other functional group. Now, the new reactions that we want to, you have seen it before, but we want to talk about, you have seen this in chapter 6, preparation of alkene, is the reduction of the alcohols. In order to reduce alcohol, what do you need to do? You need to remove oxygen, right? Remove oxygen and you add hydrogen. So in order to remove oxygen from the alcohol, we cannot do like direct reduction. This is indirect reduction. First, you do dehydration of the alcohol. You change it to alkene, and then from alkene, you just do hydrogenation to go to the alcohol. That's one method for indirect reduction. Remember, in reduction, you're adding H. Okay, you're adding hydrogen, but you cannot add hydrogen to this. You're removing oxygen and you're adding hydrogen. Which one is like more oxidized? Alcohol or alkene? Which one, A or B? Which one is more oxidized? And if you look at the definition for oxidation reduction, if you look at the definition, you're in the alcohol, going from alcohol to alkene, you are removing 2 hydrogen and you are removing 1 oxygen. So basically, removing a water or adding a water, it's neither. It's not oxidation, it's not reduction, and this would be a question on your exam, some sort of it, okay? So you will see that when you're adding H2O, you're removing H2O, it's not oxidation, it's not reduction, because if you remove 1 oxygen, that's reduction. You add 2 hydrogen, that's reduction. But if you are removing 1 oxygen and you are also removing 2 hydrogen, it kind of cancels each other effect. So in the first step, you're not done with reduction. You have to continue with this step and add the 2 hydrogen in order to get to the alkane, which is reduced form of the alcohol. And you have another example here. So alcohol indirect reduction, first dehydration and then hydrogenation. The other method that I said on the previous slide when we had that table is you tosylate the alcohol, and when you have OTS, you bring hydride ion, and the hydride ion, one of the better or the most reactive hydride is lithium aluminum hydride. The other one would be sodium borohydride. So you have the lithium aluminum hydride, you add, is going to replace the hydrogen. The hydrogen would replace OTS, and this is indirect reduction again. First you do tosylation, and then you replace with the OTS with the hydride ion. You want to make sure to remember which reagent you're using. Okay, the order of the reagent is important as well. Any questions? Questions? Okay. So as we are writing, please take notes, because when you were sitting in class, you were taking notes. Do not think that, well, the video is going to be available to me, I'm going to watch it later. You should take your notes right now and have a table or a place that you just write the type of the reactions that alcohol can go through. And every time we are bringing new reaction, you just have to add to your list. So you learn about the reactant, which is going to be always alcohol. And then you're going to learn about the reagent, and then what is the product. There are some of these reactions, if I talk about the step-by-step about the mechanism, then you are also responsible for the mechanism. That is like a stepwise reaction, study a reaction step-by-step. And in this reaction, the next type of reaction is reaction with HCl. So with the reaction with the HCl, what do you expect to happen here? You bring HCl, you have a Cl minus that would act as a nucleophile, and you have a H plus that is going to act like it can protonate, okay? It can protonate, but the Cl minus is not a very strong nucleophile. Because it's not a very strong nucleophile, so what we can do, we can bring in, we are bringing zinc chloride, and when you bring the zinc chloride, this is going to bond to the OH. The zinc chloride forms bonds with the OH, and as soon as it forms bond with the alcohol, is going to the bond between zinc and the chloride. I'm sorry, with the oxygen. Then the chloride from HCl is going to act as the nucleophile. Now you have a better leaving group. You see what's happening here? If you pay attention to this chloride, I'm sorry, the final product that you have here, this is going to tell you what's the purpose of adding zinc chloride with HCl. So we've been repeating this, that OH is not a good leaving group, OH is not a good leaving group. What can you do? You can protonate it. You can tosylate it. This is another way. Bring zinc chloride, especially if you are bringing HCl, you bring zinc chloride. When you bring zinc chloride is going to form bond with the OH and helps the OH to be better leaving group. And then your nucleophile, as it comes in and it forms bond with the carbon, since carbon cannot have more than 4 bonds, the leaving group is going to leave. This product, which is the alkyl halide, so reaction of alcohol with HCl, the product gives you alkyl halide. The alkyl halide is a precipitate, and because it's a precipitate, it's going to change the solution like cloudy. And you can say how fast this precipitate forms. You can say how fast this reaction has taken place. So this reaction is not like a very fast reaction for primary alkyl halides, even though it's going to go through Sn2 reaction, but it's not a very good, very fast reaction. If you look at the secondary and tertiary would go through Sn1 reaction. And when they go through Sn1 reaction, the carbocation is going to form first. So which one would be faster? A tertiary or secondary alcohol would go through Lucas reaction. This reaction is called Lucas reaction. Which one would go faster? Tertiary versus secondary. Going to give you like Few more seconds. Hopefully you type something there. Not, okay, which one? Secondary or tertiary? Which one would go faster with Lucas reagent? Sn1 reaction. Tertiary. Why tertiary would go faster? Because when for the Sn1 type reaction, carbocation is going to form, and carbocation that forms for a secondary carbocation is going to be less stable than a tertiary carbocation. And the faster the reaction, the faster the intermediate forms, the faster the reaction. So this reaction of a tertiary alcohol with the Lucas reagent is going to takes place right away. Secondary, it takes up to 1 minute. And then primary, it takes a long time. It takes over 20 minutes, even if it happens. Sometimes you have to heat up. So it's not going to be a fast reaction. The benefit or application for this reaction, if you are in the lab, just like the chromic acid that I said last time, I said, if chromic acid does not react with alcohol, that means that alcohol is a tertiary alcohol. And that's a question that I usually like to bring on the exam also. Sometimes I just put the chromic acid, very strong oxidizing agent, and then the structure, I'm not going to say this is a tertiary alcohol, but just put a tertiary alcohol with that, with a strong, and then a strong oxidizing agent. And often, even though I say it in class that this is going to be on the exam question, I still get it like a wrong answer, and they put some sort of product, either aldehyde or ketone or carboxylic acid or ester. It's like that is a method for identification of tertiary alcohol. If it's tertiary alcohol, it's not going to oxidize. So if you do Lucas reagent, you can identify your tertiary alcohol as well, because it's going to react very fast and it would give you a white precipitate. And primary, it doesn't react. Secondary would react between like in less than 5 minutes, it would react. So what are the limitation for the Lucas reagent, or limitation of the HX reaction? In this case, the for primary and secondary is going to be very weak, because Sn2 reaction for primary, even though it is Sn2, if it goes to the carbocation, even worse, is not going to happen fast. So it's a poor reaction. So if it goes through Sn1 reaction, carbocation forms. Anytime carbocation forms, that was for E1 mechanism. For Sn1 mechanism, there is a possibility for rearrangement. What are the different conditions for rearrangement? What are the rearrangements? Rearrangement could happen with the hydride shift or methyl shift. Do you remember that? Hydride shift, methyl shift, those are the only two possibility for rearrangement. When is the rearrangement beneficial? Rearrangement of a carbocation, it only happens if the new carbocation is more stable than the old carbocation. So if you have a primary carbocation and it can't go to secondary or tertiary, there is reason for rearrangement. But if you have a secondary carbocation, if it does rearrange and still gives you secondary, it's not going to happen. So it will not rearrange. If it's tertiary, it's not going to rearrange to go to secondary or primary. It's nonsense. So for the when the carbocation forms, there's a chance for rearrangement. There is a chance for elimination. So you get like a mixed product whenever carbocation forms. These are some of the limitation for that. So this is just an example of alcohol reacting with the HBr, and then because it's going to go through formation of carbocation, a Sn1 reaction. As soon as there's a plus charge here, then there's going to be a hydride shift, and the plus charge comes position that gives you tertiary. There's a benefit here. If you have a secondary carbocation with the hydride shift, that can change to tertiary. So basically, when we say hydride shift, that's H minus moving. That means the hydrogen leaves with the 2 electron and it goes on adjacent carbon, and it can only move by 1 bond only. Is not going to be able to move by 2 bonds. It takes too much energy. So is the hydrogen with the pair of electron that goes and replaces the positive charge. The positive charge is going to be switched. The benefit of that is going from secondary to tertiary, and that is a possibility for it. So there's always a chance for rearrangement in Lucas reagent, or formation of the alkyl halide from the alcohol. There's the rearranged product that we have here. Other reactions, because from the alcohol, you want to go to the alkyl halide. That's the reaction. It's a substitution reaction. One is formation of reaction of the alcohol, ROH, with HCl, which you have to bring the HCl and then zinc chloride as a catalyst. So you have to use this combination catalyst. You cannot just say ROH with the HCl. Now for the Lucas reagent. And then you have the ROH with the HBr will work. But there's still rearrangement possibility of the formation of elimination product. Those are the limitations for it. The other method to prepare alkyl halide from the alcohol, to use the phosphorus halide. Phosphorus halide are like the PI3, which is the P with the I2 instead. So PCl3 or PBr3. If you have any of these reagent with the alcohol, your product is going to be alkyl halide. Okay? Thionyl chloride is going to work better, because thionyl chloride, just like the zinc chloride, is going to react with the OH, and it makes the leaving group better leaving group. Okay. With the PBr3, this is just the example with the PBr3. If you, first of all, if you look at your reaction and you know that your reaction, if it's ROH plus the PBr3, is going to give you RBr. You have to recognize what type of reaction is this. Can you tell me what type of reaction it is? What happened to alcohol? The alcohol changed to alkyl halide. What type of reaction is that? Can you use the chat box to answer that, please? And if you cannot, just let me know so I could slow down for you and go back. What type of reaction is this is considered? Can you hear me? What type of reaction is this? Is this oxidation? Is this reduction? Is this elimination? Is this substitution? What type of reaction are we dealing with? Substitution reaction. Thank you. Substitution reaction. What do you need in substitution reaction? What is going to make a substitution reaction to happen faster? Like a Sn2 type reaction to happen faster. What do you need for Sn2 reaction to make the reaction faster? You need a good nucleophile and you need a good leaving group. Perfect. Okay. So if you bring the Br minus without this catalyst, the OH is not a good leaving group. So when we bring the PBr3, then you would have this bond between the oxygen and the phosphorus. So first you have the new bond forming between the oxygen and the phosphorus, and Br minus is going to leave. So you basically, you generate your nucleophile here, and a Br is a good nucleophile. Okay, so you have your nucleophile. What happened on the other side, that the OH has changed now to a better leaving group. Now, when the leaving group leaves here, the plus charge actually stays behind because you want a stable group. As it leaves, is a stable, and that's what makes this complex a good leaving group, because when it leaves is a precipitate and is a very stable compound. Okay. So the Br acts as the nucleophile. It comes as just for Sn2 reaction. Again, inversion is going to happen. The leaving is on the right side and the attack is from the left side, and you're going to get your final product. So if you start from the root, you say, okay, alcohol is changing to alkyl halide. This is a substitution reaction. I need the nucleophile and I need my leaving group. And you look at DOH and it says, poor thing, is not a good leaving group. If it leaves, it's going to come back. It's not stable on its own. Why OH is not a good leaving group? Because look at that. It's hydroxide ion. Hydroxide ion is the strongest base. So if it's a very strong base, it cannot be stable. It has to attach to something else. That's why it doesn't leave on its own. So it has to change to a better leaving group. If you have these in your mind, then this mechanism is going to make more sense to you. As long as it makes sense and you can recognize the steps, you should be fine. You don't have to always memorize every step, because like when you are taking your MCAT or PCAT exam, the questions are multiple choice questions. But if you don't understand the basic of this reaction, you will not be able to recognize the steps either. So this, and the factors that is going to make this reaction to happen in better or faster way, you need your nucleophile, you need your leaving group. With the thionyl chloride, if you look at the mechanism also, with the thionyl chloride, you are going to replace the OH. This is another reagent for halogenation or changing is a substitution reaction of OH with the chlorine. Thionyl chloride is better than the PCl3. Thionyl chloride is a good reagent. So what's happening here also, you are going to have very similar reaction as the PBr3. You would see this bond forming between the oxygen and the sulfur. One of the chlorine is going to leave, and that's going to provide you the nucleophile. And the leaving group that was bad leaving group OH now is a complex and is going to be a better leaving group. So you do have a good leaving group that is going to leave here. It's going to leave, and Cl is going to replace it. I'm not worry about the mechanism with the thionyl chloride, but I want you to understand that during the reaction mechanism, what is happening is that your leaving group is changing to better leaving group, and also this reagent creates a nucleophile in between. The benefit of these are SO2 and HCl. This reaction never reaches equilibrium because these are very easy to remove from the product side. So as long as you remove this from the product side, this reaction doesn't lead to equilibrium, and it's going to be a fast reaction. Okay, another type of reactions of the alcohol. So we talked about oxidation. We talked about tosylation, followed by Sn2 reaction. Talked about Sn2 type reaction, which is the substitution reaction, and Sn1 reaction with the Lucas reagent. Talked about reduction of the alcohol, with indirect reduction, which you either had to change to alkene first and then add H2 to change to alkane, or you had to tosylate and add the lithium aluminum hydride to change to alkane. In either case, you are reducing the alcohol to alkane by removing the oxygen. So you remove water and then you add 2 hydrogens. Net result is removing of the oxygen. For the dehydration, you have seen this reaction before. One of the better reagents for dehydration is the concentrated sulfuric acid. Is a dehydration reagent here. So what it does basically is going to change the OH to H2O, protonates the OH. So if you have the alcohol with the OH as a leaving group, and you change that to H2O, is a better leaving group, and it can be. When this leaves, then you have carbocation. When you have carbocation, then you have to either, when you, let's say you have the OH first, and then you do H2SO4, then from here you are going to get the OH2 plus charge. And you could have other R groups here, or you could have so now when the leaving group leaves here, you end up with the carbocation, or before it leaves, if it's a primary, it's going to be like a Sn2 type. If it's a secondary or tertiary, it can be Sn1 type, or formation of the carbocation. So the net result, if you have a carbocation forming here, so when you have carbocation forming, it needs to be stabilized. There are 2 ways that is going to be stabilized. Either you bring in a nucleophile to stabilize this, or you bring a base, you remove H plus. When H plus leaves, this pair of electron drops in, and it gives you a carbon-carbon double bond. Now, if you look at the condition of the reaction, for dehydration of the alcohol, if you get dehydration of 1 molecule of alcohol, you get alkene as a product. So you would get alkene. If you have bimolecular dehydration, you can get ether as a result. Bimolecular dehydration. What does bimolecular dehydration mean? I have the examples, but I'm just going to show you what does it mean, bimolecular dehydration. What does dehydration means? Dehydration means minus H2O. A unimolecular dehydration, when you have at the high temperature, let's say you have H2SO4, and then you have 180-degree temperature, OH is going to leave from 1, OH would leave, and this hydrogen would leave, so you get CC double bond plus H2O. When you have bimolecular dehydration, H would leave from 1, OH would leave from the other. So you get as H2O as the product, okay? So you have the H2SO4, but at the same time, the temperature here is 140, is not 180. If the temperature is lower at 140, you get bimolecular dehydration. So if hydrogen leaves and OH leaves, the new bond that is forming is going to be between this carbon and oxygen. And that is going to change to C, CO, CC, and then this is the ether functional group. So it depends on the temperature. The cutoff is like the 140 and 180. So you have to look for these magic numbers. So what are the steps in dehydration? I already talked about the steps. The first step is going to be protonation. So OH is going to be protonated. So for the, then leaving group is going to leave. So first protonation, second leaving group is going to leave, and then you have carbocation. When you have carbocation, on the next step, you have to remove the H plus. So you are bringing your solvent, or you're bringing a base to remove the H plus, the electrons would drop in and forms a carbon-carbon double bond. Elimination reaction, a tertiary is going to move faster than secondary, faster than the primary. Because if it goes through E1 mechanism, you will get a more stable carbocation if it's tertiary. So for the elimination is going to be that. Even if it's Sn2 type, E2 type reaction, still tertiary is going to give you better or more stable product, and it's going to move faster. So in either case, for elimination, tertiary would move faster than secondary than the primary. Okay, since there is a formation of carbocation, there is a chance for rearrangement. So you have to always be worried about rearrangement. That's one thing. And then the other point, when you are when you have a let's say carbocation forming on this carbon. Next step is removing hydrogen from adjacent carbon. This carbon has two adjacent carbon. One is on the left side, and the other choice is on the right side. So if you remove from the left side, you would get this product. If you remove this hydrogen, you would get this product. If you remove from the right side, you would get this product. So which one is a better product? Which one is more stable, A or B? Okay, I see that the answer is there. So now you have to tell me why A is more stable. Maybe you didn't see that. If it's more stable, it forms faster, and that's why it says major product. So you have 70% of product A, 30% of product B. Why A is a better or more stable product? Response? Why A is more stable? Thank you so much. It's more substituted. So A, you have one alkyl group here, a second alkyl group. CC double bond is attached to two other alkyl groups. So it's a 2R alkene or di-substituted alkene. For compound B, you only have one group attached to CC double bond, or you have like 3 hydrogens attached to carbon-carbon double bond. So this is a 1R substitution, and this compound is a 2R substitution. So di-substituted, mono-substituted alkene. Based on the SACEF rule, which you learned in chapter 8, the more substituted carbon-carbon double bond or more substituted alkene is more stable. A is more stable than B. As a result, A is the major product in this case, and B is the minor product. Okay. The steps for dehydration. So there is a possibility that you get a question like this on the exam, which you have to identify the different steps. And in different steps, if this diagram is given without any of these writings, so this would be like an A, and this would be like B, and then C. Step 1 is protonation. Step 2 or B is formation of carbocation. Basically, after you protonate OH, it would change to H2O, which is water, is going to leave and changes to carbocation. So you do have a carbocation intermediate. Step 3 is going to be removing of the deprotonation. Deprotonation, but deprotonation happens on the adjacent carbon, a carbon adjacent to carbocation. So you see the deprotonation and formation of the double bond. So you have the 3 steps. If you have 3 steps, you have 3 transition states. That means you have 3 activation energy, and the rate determining step is the step with the highest energy or activation energy, and that is formation of carbocation. So formation of carbocation is going to determine the rate of this reaction. As a result, a tertiary is going to go faster than secondary, faster than the primary. Any questions? Questions? Okay. What is happening? This is a solved problem. I do have practice problems for you, and if I have time, I will go over some of those practice problems. But I just want to make sure that, you know, even if you have a solved problem, studying a solved problem is going to help you get started with the understanding the problems, and then you would be able to solve the problem. Some of the or most of the questions that you have in the chapter assignment is going to make you go back and read the book. And that's the design of that, the assignment, to make you work harder, learn more in depth. So you have to go back to the chapter, read the session, and come back and answer the question. So steps in, this is a dehydration reaction. So what's happening? First step would be protonation. Second, formation of the carbocation. So we do have carbocation. In step 3, we have deprotonation. Deprotonation, when there is a chance, like in this case, when the carbocation forms on this carbon, there is a chance to remove hydrogen from position A or hydrogen from position B. As a result, since you have 2 choices, you will get 2 products. Then you have to decide which one is the major product and which one is the minor product. If the question asks you to write all the products, then you have to draw all the products. If the question is asking you what's the major product, then you have to only write the or choose the major product. So in order to choose the major product, you need to know that this carbon here, this product here is a tri-substituted. You have a attachment 1, 2, and 3, and the one in this case, okay, let's see. We have no substitutions here and just 1 and 2. So we have di versus tri-substituted alkene. And that is going to make the compound A major and B is going to be minor. Okay, and this is known as the Sasif product. I am sure 100% that you have learned in the elimination reaction, at the end of the elimination reaction, about the Hoffman product. And the Hoffman product is when you bring like a very bulky base. Instead of bringing like a small base, you bring very bulky base, like a tri-tbutoxide, you know, something like very bulky base, potassium tbutoxide. When you have a bulky base, then the hydrogen is going to be removed from the least substituted carbon. And if it's removed from least substituted carbon, is going to give you Hoffman product. Hoffman product is anti-Sasif. So you had Markovnikov, anti-Markovnikov. Here we don't have Sasif and anti-Sasif because someone else came up with the idea. Hoffman came up with the idea of bringing bulky base. And if you do have a bulky base, and I'm sure you agree that removing this hydrogen is going to be easier if you bring a bulky base compared to the hydrogen that is attached to secondary carbon. Hydrogen attached to primary carbon is going to be easier to remove. Okay, next type of dehydration, as I said, is a bimolecular dehydration. So what does it mean, bimolecular dehydration? OH from one carbon and H from another molecule is going to leave and is going to form water, and then your final product is going to be ether. So in this case, you have like a diethyl ether. The condition for this, the temperature must be 140. The type of reaction is the Sn2 type reaction. So steps for this, if you want to look at the mechanism, let me see if the mechanism is covered or not, but you want to sense it. You want to learn about the basic reaction, what is happening. If we say Sn2 type reaction, this is the Sn2 reactions, and then what do you need for Sn2 reaction? For Sn2 reaction, you need a good leaving group and you need a nucleophile. Okay, so you cannot expect from OH to leave. Since you cannot expect from OH to leave, then the OH must be protonated. So when the OH is protonated, we change to H2O as a leaving group, and you have a very good leaving group here, then alcohol can act as a nucleophile, and the leaving group would leave. And when the leaving group leaves, in this case, because your nucleophile is not negatively charged, the positive charge is going to stay and is going to be shared between the oxygen and hydrogen, because your nucleophile came to rescue that plus charge. So it's going to take over the plus charge. Now, this plus charge has to be removed. And how can you remove a plus charge? You cannot just remove a plus charge without adding negative charge. So you have to remove H plus. And in order to remove H plus, you have to bring in a base, or your solvent must have a pair of unshared electrons to remove the H plus. Since removing H plus in this case is going to yield a stable compound, your alcohol, which is could be the solvent, is good enough. So you don't have to bring a strong base to remove the hydrogen ion in this case, because it's going to yield to a more stable compound. Questions for me? I don't want to, you see, if you don't ask questions, I continue. If you ask questions, I stop. So I don't know what you want me to do. You want me to continue, or you want me to stop? There is a specific reaction here, is very unique reaction for the diols, and is known as a Pinnacle Rearrangement, where diol would change to ketone. So the condition for that, just know the condition for it, is like a dehydration. But at the same time, it involves like a rearrangement. This is a Pinnacle Rearrangement. So the reactant is diol, the product is ketone. Your reagent is going to be, H2SO4 at 100-degree temperature. I didn't cover the mechanism, and I will not ask on the exam, but you can review the mechanism for Pinnacle Rearrangement. Per iodic cleavage of the glycol. What are glycols? Glycols are compounds with two OH group attached, two alcohol functional group, and glycols are basically a vicinal diol. The diols that are adjacent carbon, the OH are an adjacent carbon, they are known as glycol. You could have like a geminal diol if you have like two OH on the same carbon. Not very stable, but it does exist. But when you have like a vicinal diol, this functional group is known as glycol. To prepare this, you start from alkene. You have two ways. One way is shown here, osmium tetroxide with hydrogen peroxide, and those were the reagents that you had to memorize in chapter 8. The second reagent is potassium permanganate, but is not a strong one, as I said last class, is a cold dilute permanganate. and that is going to change the alkene to diol. And you have alcohol and alcohol here. If you use a strong oxidizing agent or periodic acid, in this case, it can do oxidative cleavage and it will change to CO double bond. So basically it's going to yield to either aldehyde or ketone, depends on what you have here. If you have a hydrogen, then it would change to aldehyde. If you have like a carbon and carbon, then it would change to ketone. So when you are using like periodic from the diol, you expect either aldehyde or ketone, depends on the structure you have for your diol. Questions? Do you want me to continue or stop? So if you have your flashcards, that it would be just for reactions of alcohols, you have to put all your reaction like reduction, dehydration, bimolecular dehydration, and then unimolecular dehydration. What condition you would get bimolecular? Is it 140 degree versus 180 degree? You have the oxidation, we already talked. The substitution reaction, or you use HCl, what catalyst you have to use with HCl? HCl, you would use like zinc chloride with the HCl, or you would use like thionyl chloride. When you use thionyl chloride, you just use the thionyl chloride by itself. And you just, make the sample also reaction on the other side. The other set of the flashcards that I said, you want the list of all oxidizing agent in one card. And if you see like a new oxidizing agent, just add it. You want the list of reducing agents. And then you rank them. Is it strong? Is it mild? Is it weak? And when do you use what? So sometimes you need the reducing agent to just stop in one step. Let's say you start with carboxylic acid. You don't want to go all the way to primary alcohol. You want to go to aldehyde. And you can't use a strong reducing agent in that case. So you just have to be careful of what type of the reducing agent, what level, what degree you're using. So, okay, next, esterification. The only type of esterification that I want to talk about is the Fischer esterification, and the other two, the other types you are going to study on your own. We talked about the tosylate esters already, the Fischer esterification. Then you look at just know the general format for the ester is like you have a CO double bond and then you have a CO single bond. So CO double bond and the CO single bond. So you have your and then you have an R group here. You have an R group there. The ester is coming from a condensation reaction, basically. You start with alcohol and the carboxylic acid. Just going to put the carboxylic acid this way, COOH, and then the R group. You're combining these two to get to this compound. That's why it's called condensation reaction. Basically, you start with two organic molecules and you end up with one larger organic molecule. So that's what the condensation type reaction is. In Fischer esterification, which is the reaction of alcohol and carboxylic acid, this reaction requires catalyst. Can you tell me why do we need a catalyst here? Or can you tell me also what type of reaction is this? Is this a substitution reaction? It's condensation, but also it can be classified as a substitution, like or elimination. And I tell you, this is like a substitution reaction. Okay, so in a substitution reaction, you need a nucleophile, and you need a leaving group. Can acid act as a nucleophile or alcohol? Which one is going to act as a nucleophile? Which one is the better nucleophile? Okay, just because carboxyl group, after losing the hydrogen, is going to be stable on its own. So it's not a very good nucleophile, is not going to be very aggressive, is not going to attack something else. And in either case, you have the OH and OH as a choice for leaving group. So the OH, if the OH from alcohol is expected to leave, then we expect this to be nucleophile and vice versa. So this is another set of reaction that you learn in chapter 21 about the esterification. But in this case, I'm just going to, I guess it's better just to simplify it, say that this is a substitution reaction. You need a catalyst, because if you don't have catalyst, you're not going to have a good leaving group. So basically, the RO or alkoxide is going to come and replace the OH. This reaction is going to give you ester. The reaction is a reversible reaction. It reaches equilibrium. And anytime you have a reversible reaction, you don't have a very good yield of the reaction. It's going to be weak, is not a high yield of the reaction. And if it's not high yield of reaction, you want to change the condition of reaction. You want to make sure that you get a better percent yield. Otherwise, you would lose a lot of money over this. So this part is coming from alcohol, and this side is coming from the acid, plus H2O. One way to make this reaction to go forward is to remove water. Another way is to add one of these reactants. You use excess amount of the reactant, use excess amount of the alcohol, and that's is going to go waste. It's not cost efficient. But those are some of the suggestions that you could have. Add more reactant or remove one of the product, and remember about the Le Chatelier's principle, and say, if this happens, we expect that the equilibrium would shift the product and we are going to get more ester. So if look at these specific reactions. In the esterification reaction, the OH is basically leaving group, and then the RO is going to act as a nucleophile. Water is the byproduct, as I said. It can be removed in order for the reaction to shift toward the product. But instead of the carboxylic acid, if you use acid chloride, what's the benefit of using acid chloride? What did change? Since OH was the leaving group and is not a good leaving group, and the RO is going to come and replace this anyway, we don't need this. If we replace that, if we use a Cl, acid chloride, in replacement of the acid, now we have a better leaving group. This reaction is going to be faster. What's the other benefit? We have better leaving group, faster reaction. The other benefit is that you have HCl as the final, as a byproduct. HCl is gas at room temperature. It can escape the container easily. You don't have to force it. So this is going to be removed easily. The reaction never reaches equilibrium. This is a one-way reaction. And that's another benefit. What's the disadvantage of that? Acid chloride is very expensive compared to this carboxylic acid. Carboxylic acid, in order to change the acid chloride, you have to mix it with the thionyl chloride, the reaction, the one of the product is like SO2 and the other is a HCl, is not the easiest reaction in the lab. You cannot do it. In industry is more doable. So it's expensive. That's the only disadvantage. Otherwise, this is a very good acid derivative, or acid chloride is very good for the Fischer esterification. It can, the reaction would go very fast. The tosylation, we already looked at this, formation of the ester. So basically, you see the general structure for this. You have element that has lower electronegativity, like carbon, is attached to double bond oxygen and then the single bond oxygen. This is if you use carboxylic acid. In here, you have the sulfur, which has lower electronegativity than the oxygen, is attached double bond to the oxygen and then single bond to this, and followed by R. So RO is attached to this. So we have the Fischer esterification from carboxylic acid. You could have esters that is coming from nitric acid. You could have esters that is coming from sulfuric acid. So you can get different type of esters. So you have SO double bond, SO single bond, general format. Alcohol plus acid gives you ester. Now, if you use sulfuric acid, you have sulfate ester. If you have phosphoric acid, you get phosphate ester. If you use nitric acid, you get nitrate ester. And what happens in general, RO, which is the alkoxide, is going to replace the OH from the acid. And that acid could be the sulfuric acid OH, or it could be phosphoric acid OH. You remove this and you add the CH3O, or in general is alkoxide ion that is replacing it. And these are some of the structure of the phosphate esters that you could see in DNA. This reaction is very important. Why is it important? Because you can get these questions definitely on the exam. You will get it on the quiz, you will get on the exam, you will get in the PCAT, you will get in MCAT. It's a popular reaction. So everyone likes to talk about. Maybe is like the Williamson is a fancy name, but still is that it's just my experience has shown that you could see it in many type of the exam. At least I give this question on the exam for quiz, exam, and then final, just to add more juice to it. So how do you make ethers? In this case, using the Williamson synthesis of the ether, is an Sn2 type reaction again. So for Sn2 type reaction, you start with the alcohol, ROH. So you want, in Sn2 type reaction, you need a nucleophile and you need like a RX, right? Alkyl halide, something with a good leaving group. So if I bring the RX, I also have to have a good leaving group. So I'm going to get like ROR as a product. So if the RX alkyl halide, because those are very famous for Sn2 reactions, if one R comes from alkyl halide, which is this R is coming from alkyl halide, let's say, we see that on this side, then the other R must come from nucleophile. And there is no oxygen coming from alkyl halide, then this whole thing must come from my nucleophile. So we know this is chapter of the alcohol. we have to bring this, use the alcohol, is going to be alcohol plus, if we say alcohol plus the alkyl halide, we should get ROR. So we should get ROR. Just making RO and then R. But is this suitable? Is this good nucleophile? This is not, ROR is not a good nucleophile. Can I change this to better nucleophile? If I make this much stronger nucleophile, it's going to make this reaction much faster. So how do I change to this better nucleophile? I'm going to remove the hydrogen. How should you remove the hydrogen? In order to remove the hydrogen, you have to bring very strong base, right? You have to bring a very strong base to remove hydrogen. Example of very strong base is sodium or potassium. These are very strong base. And if you bring these two, you're going to change that to RO minus. So you get alkoxide. It's changed to ionic compound like a RONA plus, but this, if it's ionic compound, you're just looking at the nucleophile piece that you like. When the RO minus comes in, instead of the ROH, this can attack, the leaving group would leave, and you get your ether. So you have the technique, or this reaction is called Williamson synthesis of ether. What are the steps? You start with the alcohol, change the alcohol to alkoxide. How to change it? You add either sodium or potassium as a strong base. Then you would make it react with alkyl halide. Then you get your ether. The technique or the reaction is called Williamson synthesis of ethers.